Good morning, my YouTube viewers. It's Crystal here, and I want to do another code review for you. This code review is going to be on the California births dataset, and I'm going to compare the Holt Winters model to the ARIMA model because it's always important to experiment with different models to see which one is going to give you the least error, because that's what you're looking for, is the least error. So this is a time series data set of female births in California in 1959. So the first thing I want to do is I want to install the most current version of stat models, NumPy, SciPy, Patsy, and Pandas. So we make sure that we've got the most current versions of those libraries. And we have created the program in Google Colab, which is the platform that I like to use because I don't have to install anything on my computer and I can just do it all online. And so the only thing about the Google Colab that I don't really like is they don't have a very good undo function. So you have to be careful to make sure that you don't delete or overwrite any code. They do have a facility over here in Edit where you can delete cells and you can undo when you deleted a cell. But other than that, there's not a lot you can do when you delete or overwrite code, except you may be able to go into your save history, and if you go into the save history, you might be able to retrieve the code that way. But other than that, if you can't retrieve the code that way, you've lost it. So that's one thing that you do have to be careful with when you're working with Google Colab. So after we've created the program, what you want to do is you want to import your libraries. And when we import our libraries, we import them as Panda as PD, and Panda is Pandas is a data processing library that enables you to create data frames and maintain them. We import NumPy as NP, so we want to do numerical calculations, and so you're going to use NumPy and Pandas a lot in your programs. We're going to import math, which is an inbuilt library in Python, and it performs mathematical calculations, and you're going to need math when you're calculating your error. We're going to import matplotlib.pyplot as PLT, and that's a graphics library, and that enables you to plot your data points onto a graph. And we're going to import Seaborn, which is a higher level graphics library that enables you to do statistical graphics. So that's what we're going to do. So after we've imported our libraries, what we're going to do is we're going to read in our CSV file. So I've got this data set from Jason Brownlee's GitHub account. So we're using Jason Brownlee's total female births daily from his GitHub account. So series equals pd.readcsv, and then the website address. Index call 0 means the first column is going to be your index call, and parse dates 0 means that they want to parse the dates, and what that does is that timestamps your date. So you've got the date as your index, and then you've got your birth. So you've got an index column and then a birth column. So we're going to plot the data points onto a graph, and so this is what it looks like on the graph. And then we're going to do a hist plot so you can see what type of curve it makes. And so you can see we've got a few outliers, that most of the births were around 40, between 30 and 50, and then you've got a few outliers of one was 73. So we're going to get a two-side view of that if you want to see a two-side view. And then now what I've done is I've created a month column so you can see, how many births you had for every month. And you can see there's a few outliers, but you can see that in September, they tended to have the most births in September. You can do a day of the week if you want to see how many births they had on each day of the week. And I think it was Wednesday. So you had outliers on Wednesday. And because of the outliers, you generally had the most births on Wednesday. And then you wanted to check the week of the year, see how many births you had on the week of the year. It looks like maybe number week 39, you had the most births on week 39. So you can see that just gives you an indicate. These box plots give you an indicator of how many births you had in which part of the year. So now what we're going to do is we're going to drop unnecessary columns because that could potentially mess up your forecast. And so since you don't need those columns anymore, we've just dropped them. So now the data frame is going back to what it looked like when we first started. So now what we want to do is we want to check the statistics. So the maximum birth was 73, and it was the day was on 265, and so it was on September 23rd, 1959 is when they had the maximum birth. The minimum birth was on day 31, so it says it was February 1st, 1959, you had 23 births. So that's just telling you which index number you had for each day. Now what we're going to do is we're going to do some smoothing just so you can see what it looks like smoothing. So whenever we do smoothing, you can see that there is definitely a trend to the birth. So what you're looking for is you're looking for trend and seasonality, and there's definitely trend there. And what that means is a trend is long term, but that just smooths out what the graph looked like. So you can see there's a trend there. So now we do PACF and ACF. So the first thing we do is we plot our ACF. And so I watched a video on this, and he said that if you know the ACF and the PACF, you can experiment on what your parameters are. But I don't think that this video I looked at, he did a very good job at telling you how to determine what the parameters are based upon the ACF and the PACF. But if you know how to read ACF and PACF, well, there are your plots right there. Okay, so now we've got a PACF. And so you can look at that. If you know how to read the charts, that won't tell you which PDQ combinations to use if you know how to read the charts. But I just generally used it with the for loop and then selected the best parameter with the lowest RMSC from that. Then what we're going to do is we're going to check for stationarity, and I put the stationarity into a for loop. So it depends on how many columns you have, and it doesn't matter because it's a for loop. So it just so happens there was one column. So when we check for stationarity, we use the A.D. Fuller test. And then when we use the A.D. Fuller test, it said that we had 5.24 to the negative 0.05. So since the value was less than 0.05, that means that it was stationary. And then we also checked the statistics for the birth, which was negative 4.808. But what you're looking for is the p-value. The p-value tells you whether it's stationary or not. And so if the p-value is less than 0.05, it's considered stationary. And then after we've checked to see if it was stationary or not, what we do is we split our data frame. And so I decided I wanted 90% train file and 10% test file. Now what we want to do is we want to analyze our test. We want to see what the test looks like. So this is just a diagram of the test. And you've got anywhere from, 30 to 55 in the test set. Now what we're going to do is we're going to use the Holt-Winters model. And the Holt-Winters model gives you triple exponential smoothing. And so in order for the Holt-Winters file to work, the time series has to have seasons and it has to have trends. And so you don't have to, I put the Holt-Winters at the very beginning of the program. And the reason why is because you're not supposed to do any manipulations on the data set, like to take out the trend or take out the season, because the Holt-Winters does that already, and it's called triple exponential smoothing. So it does eliminate the trend, and it eliminates the season, and it eliminates the residual effects within the program, within the function, and you don't need to do that. So I set it up with seasonal periods of 12, because you had 12 months. And then if you go back and look at what the graph looks like, I just thought I would do one for every month. I just thought they would have a peak for every month, so I would just do one for every month. But if you can actually see the peaks, then you can count the peaks and you can set the seasons up for that. And then the trend was additive, so you have either additive or multiplicative. So additive is if the plot of the graph is in a straight line, and then multiplicative is if it's in a curvy line. And so since it was a straight line, I did additive. And then I fit the model, and then you can see that it printed out a survey, and so it gave you lots of statistics in the survey, telling you that it did 328 observations. And it used exponential smoothing, because that's what Holt-Winters is, exponential smoothing. And it said you got an error message saying no frequency information was provided. So inferred frequency D will be used. And frequency D means it checks it daily. So now we check our y-hat, which is your prediction. And so it gives you the values of y-hat being 44, 45, and 46. We check our error, which is 6.86. And then we compare our predicted values against our true values. So you can look and see how the predicted values compare against the true values. And then we plotted it on a graph. So you can see that there's a little bit of variation in the prediction using the Holt-Winters model. So the next thing we did was we did a seasonal decompose, and so you want to break your model up between residual, seasonal, and trend. And I suppose what I could have done is I could have put the seasonal decompose before the Holt winters because it's not really doing anything to it. So let's just put this before Holt winters. Okay, let's run it. It should not affect Holt winters because the only thing that it's doing is it is decomposing the time series and breaking it down into trend, season, and residuals. So it should not affect that. So now you've got your seasonal component. It's broken down into your trend, your season, and then your residual, which is like a noise. So you still got the same amount of error in the Holt winters, and the reason why is because the seasonal compose doesn't actually do anything to the time series. All it's doing is breaking it down. So we were looking at that. So we're looking at, you can find your, after we've done our seasonal compose or the Holt winters, what we want to do is we want to find our minimum and our maximum values. So series max is 73 and series min is 23. So you can find your minimum and maximum values. And then what we'll do here, so we're going to break it down into train and set test sets. So as I said, the train set is going to be 90% and the test set is going to be 10%. So let's just look at this. That's interesting. So we splitted our data frame there into train and test just before it went into Holt winters. And then we're breaking it down into train and test set again. So we already had our train and test set previously, but now we're going to do train X and test X. And so what we're going to do is we're going to set them up into data frames and set the index up for the month and the actual data set itself up for the column. So we've got train X and test X here, but before we did that, we set it up for train and test. So that was one interesting thing that I did, because I wanted to make sure that I had my data frame split when I used the Holt Winters. And so the Holt Winters was just train. So instead of train X and test X, it was just saying train. And then do my test as well. So I didn't really need to do train X and test X, but I did. So it wasn't necessary to do that. And then now what we do is we set up our ARIMA model. And in our ARIMA model, I did actually use train X and test X. So that was probably one thing that I needed to have train X and test X for. But in theory, you probably only needed to split your data set up once. But I didn't. So that was just a little anomaly on my part. And then now what you do is you have this code, and I put little hash marks in it to make it remarks, but here is the code where we set up the PDQ operations. And then so we set up the PDQ operations and we put it in a for loop. And then when we put it in the for loop, we check what the lowest error is. And the PDQ combination that gives us the lowest error is going to be the PDQ combination that we use. So I've got it here on the screen if you want to write down the code for finding the PDQ combinations in the for loop. So you can always stop the video and write the code down. And then after it goes through the for loop and it checks the error, it gives you it puts the PDQ combination into an array or a list called order 1, and then it puts the error into a list called RMSC. And so we take the order 1 and the RMSC and we convert that to a data frame. And then when we convert it to the data frame, we have to merge the data frame together to make it one data frame. And because we had to merge the data frame together to make it one data frame, then we've created these temp column to do that. And then after we've merged the data frame, we don't need the temp column anymore, so we drop the temp column. And then what we do is we check the min RMSC, and we look for the min RMSC, and that's going to give you the index numbers, because it says results.loc min RMSC. That'll give you the index number and the PDQ order, and then you put the PDQ order in there, and that will give you the best fit. So then we go in again, we do our stats models function again, model equals ARIMA, train X values, order equals 0, 0, 0, and we've checked model.AIC. I'm not sure exactly what model.ASC is, but I was looking on a video and it said that you want this to be a low number. So what we can do here, AIC, evaluating model with AIC. Let's see what it says. No, let's see. Just see, but AIC is one of the things you're supposed to check for. So let's just see if it says anything. The ACACA information criteria is a widely used measure of a statistical model. It basically quantifies, 1, the goodness of the fit, 2, the simplicity, parsimony of the model into a single statistic. When comparing two models, the one with the lowest AIC is generally better. Now let us apply this tool. So it's just in comparing various ARIMA models. So basically what it's doing is just you want a low score. And so like when you are testing the fit of the PDQ fit, you want to get the lowest score possible. So that's what AIC is. And then we make our predictions, and you can see that we've made the predictions here. We have an RMSC of 3.16, which is better than the RMSC that we got for Holt Winters, because I think Holt Winters it was about 6. And then we've got our data frame, and so you can compare your true values against your predicted values. So that's it for your ARIMA. So in this instance, ARIMA performed better than the Holt Winters, but let's just say is AIC, is that what we're using? AIC. So let's just see what our AIC is. It'll take just a second for it to work. So it had an AIC of 1308, but the AIC in ARIMA was higher, of 2249. So we have a little situation here where the AIC in Holt Winters is better than the AIC in ARIMA, but the RMSC in ARIMA is better than the RMSC in Holt Winters. So that is a bit of a conundrum. So I think that since the RMSC is better in the ARIMA, I probably would go with the ARIMA model, but it's a personal choice. You just have to decide which model you want to choose. So I've been talking for almost half an hour on this code review, so I'll go ahead and conclude this video. I hope you got something out of the video. I know when I finish the video, I'm going to go correct the fact that we had two incidents where we split the data, and then I'll correct that, and then I'll make a blog post on it. So that's one good thing about doing these code reviews, because when I go through and do the code review, I can find out things that I want to change in the code before I go through and actually do the blog post. So thank you so much for watching this video and helping me to do the code review and find out things that I could change to improve the code. And I would like to thank all my subscribers for supporting my channel, even when I get a little bit tongue-tied. But I hope that you appreciate data science is a very difficult subject, and so sometimes, although mentally I know what I'm doing, sometimes it doesn't come out of my mouth exactly the way I would like for it to come out. So thank you so much for supporting my channel and watching my videos, and I look forward to making more videos for you in the future.